The group of unsaturated hydrocarbons with the general formula CnH2n-2 is known as alkynes. Alkynes contain at least one triple bond between two carbon atoms. The first of the alkyne series is ethyne, with the chemical formula C2H2. Ethyne, also known as acetylene, is used for arc welding in combination with oxygen gas, which is known as oxyacetylene flame. Alkynes have less number of hydrogen atoms than that of alkanes and alkenes. Hence, though their names are different, the nomenclature of alkynes is invariably dependent on the corresponding alkane. In the IUPAC system, alkynes are named by replacing the ANE of the corresponding alkanes by the suffix YNE. For example, ethane becomes ethyne and propane becomes propyne. In a structure, the carbon atom with the triple bond is assigned the lowest number. This lowest possible number of the carbon atom also denotes the position of the triple bond. However, in some alkynes, there may be more than one possible structure because the position of the triple bond may be different in each structure. For example, pentyne has two structures, as shown here. In one structure, the position of the triple bond is 1, whereas in the other, it is 2. They are named as pent-1-ine and pent-2-ine. When two compounds differ in their structures due to the position of their triple bond, they are known as position isomers. Let's see if we can arrange the atoms in a different way to get another different structure. You can see that we got a chain structure of the same compound. Such a structure is known as a chain isomer. In this structure, the position of the triple bond is 1. Therefore, the name of the isomer will be 3-methyl-bute-1-ine. Now let's understand the structure of ethyne molecule in relation to a triple bond. An ethyne molecule has two hydrogen atoms bonded to two carbon atoms. Each carbon atom has two sp hybridized orbitals and two unhybridized p orbitals. The head-on overlapping of the two sp hybridized orbitals of the two carbon atoms forms a carbon-carbon sigma bond. The sp hybridized orbital of each carbon atom overlaps with the 1s orbital of each hydrogen atoms along the internuclear axis. This overlapping forms two carbon-hydrogen sigma bonds. The hydrogen-carbon-carbon bond angle is 180 degrees. The unhybridized p orbitals in each carbon atom lie perpendicular to each other as well as to the plane of the CC sigma bond. The two p orbitals undergo lateral or sideways overlapping, forming two pi bonds between the two carbon atoms. Hence, an ethyne molecule consists of one carbon-carbon sigma bond, two carbon-hydrogen sigma bonds, and two carbon-carbon pi bonds. The electron cloud between two carbon atoms is cylindrically symmetrical about the internuclear axis. Therefore, the shape of ethyne molecule is linear. The carbon-carbon triple bond is shorter than carbon-carbon double or single bond. As the triple bond is shorter, it is stronger compared to single and double bonds. First, let's look at the industrial preparation of ethyne from calcium carbide. In this method, initially limestone is subjected to thermal decomposition, in which it results in the formation of quicklime. Quicklime obtained is heated to high temperatures with coke to get calcium carbide. When this calcium carbide is subjected to hydrolysis, ethyne or acetylene is formed. Alkynes can also be prepared from vicinal dihalides, that is, 1,2-dihaloalkanes. A vicinal dihalide molecule has two halogen atoms, each linked to two adjacent carbon atoms. When treated with alcoholic potash, the molecule undergoes dehydrohalogenation. In dehydrohalogenation, first, an atom of halogen on one carbon and an atom of hydrogen present on adjacent carbon in the alkyl dihalide are eliminated as one molecule of hydrogen halide. This results in the formation of alkenyl halide. This alkenyl halide, when treated with a strong base such as sodamide, another molecule of hydrogen halide is eliminated, thus resulting in the formation of an alkyne. For example, when 1,2-dichloroethane is treated with alcoholic potassium hydroxide, forms vinyl chloride, and this, when treated with sodamide, forms ethyne. Do you know why a strong base like sodamide is required for the formation of ethyne from vinyl chloride? As the chlorine atom is directly attached to double-bonded carbon atom in vinyl chloride, it is made highly unreactive. In other words, as the non-bonding electrons of chlorine and the pi electrons of carbon-carbon double bond are in conjugation, the carbon-halogen bond acquires a partial double bond character and the removal of it becomes difficult. Hence, a strong base, such as sodamide, is required for the removal of hydrogen chloride from vinyl chloride to form ethyne. Alkynes follow the same physical characteristics of their predecessors, alkanes and alkenes. The first three alkynes of the series are gases. The alkynes from the 4th to the 11th in the series are liquids, while the higher ones in the series are solids. All alkynes are colorless and odorless, except ethyne, which has a characteristic smell. The CH bond attached to carbon atom with triple bond in alkynes. Alkynes exhibit some polarity, unlike alkenes and alkenes, which are non-polar. This is because the CH bond in alkynes is slightly polar due to the sp hybridization of carbon. As alkynes are non-polar and water is polar, alkynes are water insoluble. However, they dissolve in non-polar organic solvents like ethers, carbon tetrachloride, and benzene. The melting point, boiling point, and density of alkynes are directly proportional to their molecular masses. Coming to their chemical properties. Alkynes exhibit more acidic behavior than alkenes and alkenes. For example, sodium metal reacts with ethine, forming monosodium ethanide and disodium ethanide. Similarly, propene with one hydrogen atom attached to triple bond carbon atom on reaction with soda amide forms sodium propanide. Sodium metal and sodamide are strong bases and do not react with alkanes or alkenes, as they are not acidic. This shows that alkynes are more acidic in nature than alkanes and alkenes. Let's understand why. The hydrogen atoms in ethine are attached to the sp hybridized carbon atoms. On the other hand, the hydrogen atoms in ethene and ethane are attached to the sp2 and sp3 hybridized carbon atoms, respectively. The sp hybridized orbitals of carbon atoms